Okay, it's a couple minutes past the hour, so let's go ahead and get started. Sorry. Leaf blower outside. Okay. Hi, I'm Jeff Carlin. I will be leading today's Delegate Assembly on behalf of the Community Engagement Team. Welcome to the third DP0 Delegate Assembly. Today, we're going to have a demo of some, in fact, two image display notebooks. And so while we're getting set up, people are welcome to, or encouraged, I should say, to suggest topics for breakout rooms, the second half of today's assembly. As we have in the previous ones, we will move into breakout rooms. So these breakout rooms can be of your choosing. So if there's a topic you want to explore, one of the tutorial notebooks you want to explore in detail with others or discuss, suggest breakout topics in the chat, and folks from community engagement team who are monitoring the chat can collect those suggestions, and we'll add them to the list here, and then I can create breakout rooms once we're done with our with the tutorial half of the assembly, and we can head out into those breakout rooms. So one possible follow on to the discussion of image display that we're going to have during the first hour is people might want to go and explore those notebooks in more detail. So that's one possible suggestion. I know we've had a large scale structure working group that has met at previous breakouts. So if people would like to continue that, we can definitely do that. And if there are other topics, again, please suggest those. Glad to see many more people still arriving. Welcome, everybody. I had just a couple more notes I wanted to make. Many of you probably attended the Project and Community Workshop, the annual meeting. There were, I think, it was over 600 or 700 registrants for that meeting. It was a virtual meeting, of course. If you attended that meeting and you haven't yet done so, please fill out the feedback survey. This will help us to improve our planning process for future workshops. So the link is here, the short link is given here, or you can also hold your phone up to your screen right now and scan the QR code. And I also wanted to note that that the sessions were all recorded and those videos are available for you to watch. So you can either go to the workshop website, which is this project.lsst.org/meetings Rubin 2021, but you'll need to log in if you are a registered attendee. But you can also go to, and you can even subscribe to the Rubin Observatory YouTube channel, and the videos are also from the PCW are also available on that YouTube channel. So I would encourage you, if you want to know more, if you were unable to attend the workshop, you can go there and learn more. And one final note before we get into a super fun tutorial. Besides these delegate assemblies that are every other week on Fridays during this time, I also wanted to highlight that we do have third Thursday office hours, which are scheduled at a time that is friendly for our Australian and East Asian colleagues. So I encourage you to drop in. Many of us from the CET make ourselves available and are there for discussions and to answer your questions. And also I wanted to note that in the intervening weeks between the delegate assemblies, you as DP0 delegates are all welcome to attend the Stack Club, which is an informal 2-hour session where we get together and work on projects related to using the RSP and the Rubin pipelines to explore science questions or just learn how to use the science pipelines and related tools. So wanted to encourage you all, you're all welcome to join the Stack Club, and that takes place, again, in the intervening Fridays at the same time as these delegate assemblies in the same Zoom room. Okay, and I also want to encourage you all to, if you want to follow along with the presentation, the tutorial, you can log in to the RSP at data.lsst.cloud and open, you should have 2 updated notebooks in your tutorial notebooks folder. And there is notebook 3, which is image display and manipulation. And then we added a 3B to explore image display with a different tool called Firefly, which you'll see in a few minutes. So these 2 are the tutorials that we're going to go through today. So again, at any time, if an idea for a breakout comes to mind, feel free to suggest those in the Zoom chat. And of course, if you have any questions, also post those in the Zoom chat. And people are here from Rubin and from the community engagement team to help answer your questions. Before we get on to a tutorial, did we have any questions right now?
None yet.
I'm hoping that leaf blower outside is not too much background noise.
I can't hear it since you shut the window.
Okay, good. It sounds pretty loud from my vantage point, but okay. Good.
Okay, I hear it a little bit.
They, at some point, they have to have blown all of the debris away, right? Like, how long can it go? Let's see, now I have to find my window. Okay, and now hopefully, can you see a Jupyter notebook in the science platform? Excellent. Let me make sure I have the chat handy. Great. Okay, so the tutorial today, again, these are notebooks that are available to you to go through in more detail on your own time, but we wanted to show you ways to look at images. One of the first things, I don't know, if I go to a telescope and take some data, one of the first things I want to do is look at the awesome images that we just took. And as I'm sure you all do for the DP0.1 data. So let's go through a little bit about the tools that are available to you to examine the DP0 images in the science platform. So we're going to go through, as I mentioned, 2 different notebooks briefly that highlight 2 different ways of using what's known as the astronomical framework, AFW, display library. So the first one here, we're going to do this with static images in the notebook using matplotlib, which is a standard Python plotting library. So this, hopefully, yes, okay, good. So this, as I mentioned, we're going to set up at first the AFW library and the butler, which you've probably seen before, which is in the daf.butler, and that's what we use to access the images. So we start off, and first we're going to do the very basic setup, which is just checking that we are using the current weekly release of the, or the current recommended release of the science pipelines. And then we're going to import some common Python libraries, including matplotlib, which will be, you'll see this a lot in this notebook. We're importing matplotlib.pyplot as PLT, so plot. And we're also going to import the AstroPy WCS, the World Coordinate System function. You'll see how we can apply that to the images a little bit later. The next couple of cells are not super important. This is just to prevent some warning messages that print that we don't necessarily want to see, but it is not a huge problem. One additional thing that we recently added is we found an issue where matplotlib stores the data arrays from or associated with the images that it plots. And so if you keep running cells in a notebook like this, these large, if you keep running the cells that plot these large images repeatedly, eventually you run out of memory and your kernel dies. And so we wrote a brief garbage collection function that we run at the end of each plotting cell to clean up that memory, free up that memory. And it should also help sort of the performance within your notebook, perhaps. And so that's all this is here, where it just says go through and remove the image, clear the figure, close the figure, and then run the garbage collector. So that's not super important that you understand the details, but it's to make things not crash for you. And then we're going to move on to just setting up some plotting defaults. And this is just to make your plots look spiffy. You don't have to do this. This is just setting some of like the font size and the line widths and things to make your plots look really beautiful. You can play around with these as you wish. But now let's get to the fun part, which is, okay, we're going to load the science pipelines. And you've seen this before, where you load the butler, which we use to access the data products. And we're going to load, as I said, Afw.display. And so we'll call that Afw Display. And that's what we're going to use to access the image plotting and visualization routines. And so the first thing we want to do is load some data. So to do this, we need to tell the butler, give the butler a data ID that uniquely specifies some image. And so in this case, what we're going to do is we're going to give it a visit number. So each sort of exposure is assigned a visit number. And then we're going to pick just one detector from that visit. And we're going to tell it the filter, which actually is already uniquely defined because the visit number was taken with this band. But this should be enough information to retrieve an image. And then we go and we initialize, and I think we've seen this in previous tutorials. But we need to initialize the repository where the data live. And then we need to tell it which collection from that repository that we want. And then we initialize a butler. So we're just calling the butler function that we imported before, and we point it to that repository and tell it the collections that we want it to have access to. And then we're going to get a calexp, which is a calibrated exposure. Typically, we call those process visit images, PVIs. You'll see that quite a bit too. But this is just the processed, the flat fielded, bias corrected single visit image. So we've loaded now a calexp. So now we want to actually look at it. So what we're going to do here, and you'll see a different version of the same line in the cell that I've highlighted here. We're going to use Afw Display, as we mentioned. And basically, we need to tell it where to send the plots. So the next thing we want to do is tell it set the default backend to use matplotlib. And you'll see the results of using a different backend in a little bit. We're going to use Firefly a little bit later. And another possibility, although not in the science platform, is DS9. But Matplotlib or Firefly are going to be your best bets for now. Okay, so we set that backend, and now we're ready to display the image. And for those of you who are familiar Python users, you'll recognize a lot of this. But basically, we first have to create the figure by initializing this plot.subplots. And so we call that, we create an object for the figure and for the axes separately. Once we've initialized that, then we need to create this alias to Afw Display.display. And you can see that we've pointed it to this figure that we initialized. And so now we have this display object, and we can do things, although you don't have to do so. You can set the image scaling, for example, and we'll experiment with this in a little bit. But you can set the scaling. This is a standard hyperbolic sine async scaling. That's setting the color stretch. And the range is set by, this is another sort of standard astronomical algorithm to do the z-scale. And then we finally use this method called MTV, display.mtv, to load the image in the display. So then we're going to use the calx, which you remember we loaded up above. We're going to use calx, and then we're going to use only the image portion of that, and you'll see why we did that in a little bit. So let's shift return, and ta-da! You see an astronomical image of some piece of sky. And so now we can say, well, we're all done. Let's quit for the day. That was great. Or we could continue and try manipulating this image a little bit. So remember I mentioned we imported that WCS library above. So if you want to convert from these pixel coordinates, you can see this goes 0 to 4,000 in each axis. Those are pixel values. If you want to convert from those pixel values to sky coordinates, we use the world coordinate system. And so you need to get the transformation that is associated with this image that has been calibrated to known objects with known positions. So to do that, we're going to use that WCS package, and then we're going to use a method associated with that calibrated exposure called getWCS. And so we're going to get its solution, its WCS solution, and apply that to project the image to the sky. And so let's try that. And the rest of this is similar to what you saw in the previous cell. Oh, and we added a pretty grid on top. But now you can see it's projected to right ascension and declination coordinates. And just to show you what this this WCS object looks like, oops, if you create a new cell, I did that right, yeah, good. So this is what is being applied, and if you're, an observational astronomer, you probably recognize all these standard Fitz header values. So these are defining the solution to go from pixel to sky coordinates. So this just shows you a way that you can access that and see what those values are. Okay, well, that's really great. Now we have it in sky coordinates. Another thing you may have noticed is that this image doesn't look exactly the same as this image. And that's because of the scaling that we applied. So this one is scaled differently because we specifically applied that. And here by default, it's doing a linear scaling. So we may want to explore how to manipulate that a little more. But before we do that, I just want to just pause and make sure we don't have any questions. Hopefully people are able to get the notebooks to show up okay.
Yes, that community post link was good. Thanks. There were no other questions yet.
Awesome. There's still a landscaper outside making lots of noise. Hope it's not too distracting for you all. So this part is more of a matplotlib instruction here where we say, oh, you may often want to plot two images side by side. So you can, and this just shows you how to do this in case you're not familiar with matplotlib, where you create subplots. And so this just says create one row, two columns within this figure. And so now in this one, we're going to display calx.image in the first, and we're going to display calx.mask, and we'll see more about that in a minute, in the second frame. Hopefully, yeah, there we go. And so now you can see again, these are in pixel coordinates from 0 to 4,000. This looks like an image of the sky. This shows you the mask plane. So these are different bits in the plane that another image plane that is associated with the calx that encode things like which pixels are part of detected objects, which pixels are part of saturated stars or bleed trails or things like that. So we'll get into that in a little bit more detail. So let's just try displaying the image as you saw on the left with the mask overlaid on top of it. So that is this object called a masked image. And then we wait patiently, and ta-da, you can see the masked image, and you may barely, it might be hard to see over Zoom, but you may be able to see, for example, those red streaks that were visible above over here in the mask. And you can see that all of the astronomical objects have blue halos around them. And we'll explore what that means in the next section. So that just shows you a little bit about how you can explore the different image planes that are associated with each image. So that, they're also, besides a mask and an image plane, there may, with some of the image products, be a variance plane and other such things. So that just shows you that you can access each of them separately, or you can see them together. And we'll see more about this in the Firefly demo too. So that was really great. Now you know how to display an image. But now maybe you want to know more about that mask plane. So we have a section here where we go and actually do some more manipulation, both of the mask plane and of the image stretch and scaling, for example. So so we'll do the same thing we did before, where we do the same steps to display the image. And we're going to do the scaling just like we did before. You saw how you could explicitly set the scaling here. But let's set a couple of other things. Let's set the transparency of the mask plane. So this is just in percentage. So it's called set mask transparency. So it's easy to remember, because if you say 100% transparent, it should look like there's no mask. So this is in percentage, 0 to 100. Also, if your notebook doesn't say that, if it says it goes from 0 to 1, then if you pull a new version, it should update to be correct, because I noticed yesterday that it was incorrect and just pushed new changes last night. But okay, so I said 100% transparent, so there's no mask. If I say 40% transparent, then we should get back the blue halos around all of the objects. Indeed, we did. And you can see here that we explicitly set the mask plane color for a mask bit called detected. So those are pixels that are part of detected objects, detected sources. And we explicitly set that to blue. So we can even try here. Well, what's another named color? Magenta. Let's try magenta. And yeah, you can see you can actually control the color of the different mask planes. Another thing you can do, we'll set this to be a little more transparent. Another thing you can do is you can control the scaling of the image. We were using the 1/8 inch scaling. Let's try a linear scale instead, which you saw above. So now you can see the centers of objects look more peaked than in the 1/8 inch scale. So you have access to all of this information from the different methods associated with AFW display. And so you can, for example, access all of those methods. Let's just go ahead and do this here. You can say, get me the dictionary of all of those mask plane colors, for example. And so that's what is done here. And you can see that these are the colors that you were seeing above. So I think we saw some red, those were bad pixels. You can see things like saturated is green. And remember, we just set detected to magenta. And now you can see that shows up here. So this is a way that you can see the dictionary of those mask plane colors by using this get mask plane color. And then the second thing we do in this cell is we say, this is how you can get help for any of the methods associated with AFW display. You can just say help AFW display dot set mask plane color. And when you do that, that's what this is. Oops, that's what this is showing you here. That shows you how you can set that mask plane color. You need to give it a name for the mask plane and then a color for it. And one thing I wanted to highlight here is you can also tell it if the color is set to ignore, then it will basically turn off that mask plane. And so you can do this for any method associated with AFW display. And we actually illustrate that here, with some, this is a way of sort of getting a list of all of the methods that are associated with AFW display. I will also highlight that if you're not super familiar with Python, you can also, or if you don't feel like writing code, you can say display dot, and then if you hit tab, it will give you a drop-down list of the methods associated with AFW display. So you can see that we have, set the default backend, you have set the mask transparency. So these methods, they're sort of different ways to see the list of methods. And so then when you see, if you want to know more, for example, about, okay, I see that there's a scale method. If I want to know more about it, then I can just say help display.scale, and it'll tell me the required and optional keywords to invoke that. So we can do that again for MTV. Remember, we used MTV before. Has nothing to do with that TV channel that used to play music videos. but in fact, it is named after Mirella Freni. It's from Jim Gunn's image processing back in the day. So I'm going to stop there, and I'm going to leave it as fun exploration for you all to go further and say, how do I extract a cutout image? And if you go even further on, we actually create a color image made up of 3 different images and 3 different filters that are assigned to red, green, blue channels to make a color image. So if you want to see how to do that, and this is really, there are probably other ways of doing this too. These are just examples of the types of things you can do. So you can explore this a little further. And also the image that is used for this section, I will tell you, has a really beautiful galaxy cluster in that image. So if you want to see an image with a beautiful galaxy cluster, a really rich galaxy cluster, this data ID will get you there. But we're going to stop here, and we're going to switch over to showing you a different way to display images. But before we do that, I see there are a couple of questions going on in the chat, but I also see that.
I think they've been answered.
Excellent.
Yeah, there's still some concern about getting a new notebook. So everybody needs to follow the instructions that are on the community post for that to figure out how to get new notebooks and stuff.
Yeah, and if you're still having issues with that, we can work on that during the breakout time too. Yeah, if you completely log out and log back in, you should get the new version. Yeah, the one, the 0 to 100% transparency, that literally was last night that I changed that. So yeah, you may not have pulled the updated version yet. Were there other questions?
There were, but it looks like Simon answered it.
Okay. Excellent. And I encourage you to play around with this notebook, change things up, look at different types of images from the stack or from the DP0 data set, and have fun with it. Okay, and then the next part, we're going to show you a different way of doing this. And for some people, I think, working in a notebook, typing Python commands is comfortable. For others, that may not be so comfortable. You might be more comfortable with an interactive display tool. So now we're going to show you a way to use the same Afw display commands that we used, but then once you display the image, it will appear in the Firefly image display tool. And there are links in this notebook to more information about Firefly, but Firefly is used in many sort of online archives as a visualization tool, and it will be available from Rubin Observatory tool, or with Rubin Observatory tools, and via the RSP in the future. So I will say I've been learning a lot in the process of DP0 about Firefly, because I am more used to doing things in the way that I just showed you. And so now let's go through that and show you. Basically, we're going to look at the same image that we did previously, but we're going to display it with the Firefly tool. And hopefully this is one of the reasons we suggested a possible breakout for advanced image display, because you might become intrigued once you see some of the tools that Firefly has and want to play around with it some more. So what we're going to do here is we're going to do the same thing we did in the last notebook. We check what version of the stack we're using, and then we load same tools that we did. Afw Display, which is what we use to visualize images, and the butler, which gives us access to data products. And then we're going to, this is the exact same cell as in the previous notebook. We're going to load the same visit, same detector image, and we're going to get the CalExp, the processed visit image, or CalExp. And that's going to take a second. And we can ignore this warning. That didn't appear in the last one because we had that cell that said ignore warnings. Okay, so now we're going to create a display that is setting the default backend to Firefly rather than Matplotlib. And so when you execute this cell, you'll actually see a new tab appear in the RSP. And so that's happening because of this Afw display .display, and then you give it a frame number. And once you've told it to set the default backend to Firefly, that says open Firefly in a new tab. Ta-da! Firefly is ready and waiting for you to access it. Now, here's one thing you can do. You can toggle between the tabs like this, but another nifty feature of the Jupyter Notebook server is if I click and grab this tab and drag it, I can make it occupy the top half of the screen and have the notebook in the bottom half. I can also have it, occupy the right half and the notebook in the left half. So we're going to do that briefly. I apologize that I'm working on my laptop, so there's limited screen real estate. So we might have to go back to full screen at some point. But this is just to show you that when I execute things in this notebook, the image will appear over here in the Firefly window. And all we have to do now is we don't have to do all of the plot setup and manipulation commands like we did in the previous notebook. All we have to do here is just say mtv display.mtv CalExp. Oops, and don't jumble it around. So if I click that, you see very quickly, hopefully, an image appear over here in the Firefly window. So this is really nice, especially if you have a lot of screen real estate. If you could put them side by side, then when you execute something here, you can see the changes immediately. But you may recognize that this is the same image that we were looking at before. And now, if you're familiar with using tools like DS9, you may also know some features like if I use the scroll wheel on my mouse, for example, if I just scroll, I can zoom in and out on that image. I can click and drag to pan around the image. And you can see, you can zoom all the way in to see individual pixels. And we're going to explore a little more about Firefly, as many of these menu options above. But first, let's see, I see this question. So when you, I believe that when you launch a server, this is an answer to Tom's question. I believe that when you launch Firefly, it's always going to appear in a separate tab. And so you can keep that, in full screen mode and just toggle between them. But I think or you can do as we were doing and put it in half of the display. But I think, I'm not sure if any of the Firefly developers are on to give a better answer. But you can, when you have these, when you have these in this mode, you can easily just toggle between them. I know that's not exactly what you're asking, I think, Tom, but.
There was also a question. It is also possible to use DS9 as backend. Yes, but not PDF. Okay, that might be answered already.
Yeah, DS9 can be used, but not, not in this Google Cloud instance. Okay, excellent. Yeah, sorry if I was doing that a little quickly. I should. It's a little hard to illustrate click and drag, but yeah, this is the way you can change the display. For example, if I want this to be the bottom half instead of the right half, is I click this tab at the top and I drag it to the bottom, and now you can see that it's taking up the lower half of the screen, which is not super useful in this particular case. And then you drag it so that it fills the whole area. You can see that kind of bluish transparent box. When you drag it so it fills the whole area, it will then go back to the full screen. And so you can do this also, I should say. It doesn't apply only to Firefly. So if you're working on two notebooks side by side, for example, you could do like this. So, I could directly compare notebook 3 and 3B side by side. And then I can just drag it back to the full screen. There we go. So that's not unique to Firefly. That's a feature in Jupyter Lab. Okay, so now we're going to move on to similar things like what we did in the previous notebook. We can do things like set mask transparency, for example. And you can see when I set the transparency to 80, it got more transparent. You can see the astronomical objects peeking through a little bit. And you can see other things, like you can set the scaling to use an 1/8" stretch, and you can explicitly give it the min-max values like so. Okay, you can see that dramatically changed the scaling. There you go, it took a second. Or you can have it use an algorithm like the z-scale. There you go. And again, this next part is just the same thing that we were looking at in the previous notebook, where you can say, well, what do those colors mean? And you can have it print those to the screen. So, as we saw before, the detected pixels, pixels that are part of detected objects are colored blue. So that's why there are blue halos around everything. And for example, if I zoom in, you'll be able to see, oh, look, the edge is all colored yellow. That's because this is the edge flag. So that's handy. You can still access all that information. But what I want to show you next is that you also don't have to do that programmatically. You can do that directly within Firefly. And so you can see all of these buttons at the top. And you can also hopefully see that as I mouse over one, at the far right edge of the screen, over here in this blank space, you see when I mouse over this, it says show fits header. If I click on it, it will show the fits header, obviously. And so you can explore all of these different tools that are available to you. But the one I want to highlight right now is this one that looks like a stack of things, squares. This is the overlay display. And so the mask is being overlaid on top of the image. So if you want to see things, see information about the mask, if you click on that, you can now see that the mask plane colors are shown here. So you can see detected is blue, cosmic rays are magenta, the edge, as we saw, was yellow. And so that, again, I'll click out of this. And so that was this overlay display. And this is really a useful tool. And you can see in all of these that there is a clickable color menu here. So when I click on that, I can actually go and pick a color to assign to this mask plane for the detected objects. So let's make them orange. Okay, why not? You can also see that there is a checkbox next to each one. So I can toggle each one of them on and off using those checkboxes. I can also have it, I can just click hide all of them and it will uncheck all of them, and then show all, it will show all of them. There we go. Before we go on to that, right, another thing we did in the previous notebook is we displayed a coordinate grid in sky coordinates. So you can see if you mouse over this one with the, where we go? This one with the NE, this is just showing you the directions of north and east. So you can see north is downward, east is to the right. And then this one next to it says add grid layer to the image. Nice. So we have a grid with coordinates. Now again, going back to this overlay display, or yeah, this overlay tool, you can see that the grid, because it's now overlaid on the image, shows here. And you can see that this has defaulted to showing coordinates and galactic coordinates. I think that's because the last time I played with this, it remembered what I did last. But I can also show equatorial coordinates. You can see 3 hours, 32 minutes, et cetera, et cetera. I could show equatorial in decimal coordinates, 53.1 degrees. You can even do things like ecliptic coordinates or supergalactic. Great fun. So again, that's using, you can see this grid layer, and then this overlay display is going to be your friend quite often. And so, and you can also see I can change the color of the grid. Let's do it just for fun. Let's make it blue. Okay. Okay. Finally, we want to show you, oh, I see a raised hand from Simon. Go ahead.
Yeah, I'm just wondering if we can make, there are a couple of like just user issues. I'm wondering if we can make a breakout room for troubleshooting.
Oh yeah, should we go ahead and do that right away? Maybe maybe Leanne or Tina, since you all are co-hosts, would you be able to make a breakout room?
Tina, do you want to have a go?
Yes. Sorry, I was typing.
You're doing
Yeah.
many things. Thank
Yeah.
you very much.
Okay.
Great. Yeah, thanks. Okay, the last thing we're going to do is we're going to actually load a source catalog and display those sources on top of this image. Oops, sorry. Okay, so this is the section here that says plotting sources on the display. So remember, the butler is the tool that we use to access data. The catalog that's associated with the CalX, the process visit image, is the source catalog. So this is the information about all of these SRC. These are the sources that were detected in the CalX. So you can, if you give this method, this butler.get, if you tell it, I want the source catalog, and you give it the same data ID that we defined up above, then it knows that this is the source catalog associated with this CalX that we are looking at over in the right-hand side. Before I go on, I'm gonna turn off the mask here. Oops. I don't want to hide all. I want to hide just the mask layers. Okay. Excellent. So we're going to load that source catalog, and this is an object, a data set type known as a source table, and we explore these in other tutorial notebooks that you'll see in your tutorial notebooks directory. But you know, these can be manipulated in many ways, just like, you know, using common Python functions and using tools like we showed you in the previous notebook, where you can you know, list all of the associated methods that are associated to this source object. But you can do, you know, simple Python things like, what is the length of this? Okay, there are 2,440 sources in the catalog associated with this image. And you can also, actually, let me just illustrate for you the difference. In the next cell, you may be familiar with using AstroPy tables. This shows you you can actually just visualize it, see a nice HTML rendering of it as an AstroPy table by just using this method source.asAstroPy. But I'll show you what it looks like if I just type source, shift enter. You can see this is a AFW table source catalog. Okay, you can see the information there, but if I do it as AstroPy, then you get a nicely formatted, and you can image that you can actually, or yeah, it is actually an HTML image of this, I believe, is this table that you can actually scroll and view all of the columns, because there are hundreds of columns. So that's a very handy way of visualizing the contents of the catalog. But what we want to do is actually display those sources on top of this image. So let's go back over here and make it, okay. That's a pretty good view of the image. So we're going to, again, use AFW Display to send information about those sources to the plotting backend, to Firefly. One sort of funny thing that you have to do, I guess you don't have to, but it is better to do, is that basically the AFW display, when you say plot a dot, this AFW display dot, it plots one at a time. And so if you want to display all of them, you can actually enclose this for loop that loops over all of the sources. within this AFW display buffering. And so that just does all of this within a buffer. And once you've reached the end of this for loop, then it plots all of the sources all at once. So that's the reason for this buffering. So if we execute this, let's see what happens. Ta-da! You saw a bunch of orange things appear. And that is because over here we said, okay, display dot dot, and we said, okay, make a circle. That's what this is saying. That's the symbol type. And we give it, oh, I should say we are looping over each record in the source catalog. So for each one of those records, we use this method to get the X coordinate, because remember, this is in pixel coordinates, XY coordinates. So we get the X coordinate, and then we get the Y coordinates. So this is giving it the XY coordinate. We tell it what size symbol we want it to plot and the color. So we could, we can change this color as we wish. Ta-da. Okay. So yeah, that's just looping over. So you can imagine you could create subsets of sources, for example. So in the other image display, or actually in this one down below, you can create different subsets and display them with different colors, for example. And Natasha just asked an excellent question that one of my colleagues asked yesterday too. We'll come back to that in a sec. Actually, I may not even know the answer. And then finally, I just wanted to say that if you want to get rid of those again and go back to your clean, beautiful image, you can use AFW display dot erase. We'll come back to Natasha's question in a sec here. But also, as we've illustrated, you can use this programmatic way of erasing all of the sources, or of course, you can go, that's not what I wanted. I want full. There. Or, of course, you can use this overlay menu and go in here and say, okay, I'm just going to unclick those DS9 regions. So you have multiple ways, it's kind of flexible what you can do here. Actually, so the answer to Natasha's question, I'm not totally sure why, for example, this object does not show up in the source catalog. Maybe somebody with more pipelines expertise could explain why that would be. I also wanted to, I just realized one thing that I didn't highlight before, that when we were setting the scaling, using the .scale method, you can also do that with these menus that are available as icons at the top here. So you can see here, quickly change the background image stretch. So if I click on that, this gave me the same options that we were using before, like Z-scale, linear, Z-scale, ascent. So you can actually change that. You can either do it as display.scale, or you can set it here by, like, if I want a linear stretch. Wait patiently for it to calculate that. Ta-da. And actually, I really don't have an answer to Natasha's excellent question of, like, why this bright source doesn't have a circle around it, or or this one. Yeah,
that is a good question, and I'm just looking at it and thinking about it. I mean, maybe bear in mind our pipelines are still in development. Maybe it wasn't detected. It's very hard to understand why a source like that wouldn't be detected. Maybe there's a bug somewhere. I think that we should pick that up and try to work out what the problem is. I can't give you an answer. I don't know if anyone from desk is on who might have any other suggestions.
I mean, my guess is that these are, oh, actually, if we put the mask back on, I was going to say, my guess is that these are saturated pixels, many of these.
But there are other sources that look quite similar that are detected.
Yeah, I wonder if that display, you know, they look similar to the eye, but maybe they're not. Oops, no, the detected pixel gone. There. Yeah, I guess it doesn't show up with the saturated flag. This one actually does show saturated.
Yeah.
That's what the green is. So it is an interesting question. That was, yeah, I don't know why. Yeah, cool. So yeah, I encourage you to go and explore the many options that are available up here. For example, I also didn't highlight that there are these zoom tools, so I can use those instead of using my scroll wheel on my mouse. I can use these to zoom in, zoom out. This one zooms it to fit to the frame. This one zooms it to the original size and other such things. Oh, and if you really want, you can go to this thing that looks like a painter's palette and apply some quite sometimes quite garish color maps, but these are many of these are color maps that you're familiar with, right? These are standard color maps, and you can control the scaling, the bias and the contrast and the other settings as well. Or for example, if you like sources to be white on black, a black background instead, you have control of that. So I encourage you, this notebook has another portion that is complementary to Notebook 3 that displays the image that I mentioned that has a beautiful galaxy cluster, and then explores plotting different subsets of sources, overplotting those with different colors. So I encourage you to explore that as you wish. I'm going to stop here where we were, but I'll just show you, since I teased about that image, I'm just going to go ahead and show you the nifty image with the huge galaxy cluster, which we explore in both of these notebooks. So I encourage you to go and explore this more. But for now, I want to stop and see if there are any questions and whether there are any suggestions for breakout rooms.